Introduction. Imagine a world where the pyramids of Giza are not mere tombs, but celestial observatories whose mathematical proportions still challenge our modern computers. Where the golden ratio, often attributed to ancient Greece, adorns the temples of Karnak millennia before Euclid. Where a 3,600-year-old papyrus contains the key to geometry, algebra, and astronomy. This world is that of Kemet, ancient Egypt, where mathematics and astronomy were not separate disciplines, but the pillars of a civilization that inspired humanity. As future leaders of Africa, you must understand that African science did not begin with colonization. It shone on the banks of the Nile, and its brilliance still illuminates our quest for intellectual sovereignty. Prepare to deconstruct Eurocentric myths and rediscover the mathematical and astronomical heritage of our ancestors. Fundamental notions. The Rhind Papyrus, an ancient mathematics textbook. The Rhind Papyrus, dated to around 1650 BC, is one of the most important mathematical documents of antiquity. Discovered in Luxor in 1858 by Scottish Egyptologist Alexander Henry Rhind, it is housed in the British Museum, BMEA 10057. This papyrus roll, 5.5 meters long and 32 centimeters wide, contains 84 mathematical problems covering arithmetic, geometry, algebra, and trigonometry. It was written by the scribe Ahmose, who states that he is copying an older document from the reign of Pharaoh Amenemhat III, 12th dynasty, around 1800 BC. The Rhind Papyrus uses a decimal numbering system, with hieroglyphic symbols for powers of 10, a stroke for 1, a heel bone for 10, a coiled rope for 100, a lotus for 1,000, a finger for 10,000, a tadpole for 100,000, the god half for 1,000,000. Fractions are expressed as sums of unit fractions, of the form 1/n, a method that has fascinated modern mathematicians. For example, 2/3 is represented as 1/2 plus 1/6. Problem 79 of the Rhind Papyrus is often considered an ancient version of the 7 Old Men problem or geometric progression, foreshadowing mathematical sequences. The Egyptian golden ratio, divine proportion in architecture. The golden ratio, denoted phi, is almost equal to 1.618, is a mathematical ratio that appears in many Egyptian constructions. Contrary to the common belief that this concept was discovered by the Greeks, Euclid mentions it in his Elements around 300 BC, the Egyptians already used it in the design of their pyramids and temples. The ratio between the height and base of the Great Pyramid of Giza, Khufu, is 1.618, as demonstrated by studies by archaeologist Flinders Petrie, 1880 to 1882, and the work of mathematician and science historian George Geverdes Joseph, The Crest of the Peacock, 1991. The Egyptian golden ratio is linked to the concept of sect, or sect, a unit of slope measurement used by architects. The sect is defined as the horizontal displacement required for a vertical rise of 1 cubit, about 52.3 centimeters. For the Pyramid of Khufu, the sect is 5.5 palms, i.e., 5.5/7 of a cubit, which corresponds to an angle of 51 degrees 50 minutes, giving a height-to-base ratio of 1.618. Egyptian mathematical texts, like the Rhind Papyrus, do not explicitly mention phi, but the proportions of the monuments show an intuitive mastery of this ratio. Astronomical alignments, a celestial science. The ancient Egyptians were accomplished astronomers. Their knowledge allowed them to predict the Nile floods, calendar religious festivals, and orient their monuments with astonishing precision. The Temple of Karnak, for example, is aligned with the sunrise at the summer solstice. The Pyramid of Khufu is oriented with an error of only 3 arc minutes from true north, a precision that was only matched with the invention of the modern compass. The Egyptian calendar, based on the solar cycle and the star Sirius, Sothis, had 365 days, divided into 12 months of 30 days plus 5 epigomenal days. The observation of Sirius was crucial. Its heliacal rising in July announced the Nile flood and the beginning of the agricultural year. The Egyptians also knew the planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, Saturn, and the constellations, as evidenced by the astronomical ceilings of tombs in the Valley of the Kings, e.g., Tomb of Senenmut, 18th dynasty. Deepening Egyptian geometry. From field to temple, Egyptian geometry was practical and utilitarian. Surveyors, the rope stretchers, used knotted ropes to measure fields after the Nile flood. The Rhind Papyrus contains problems for calculating areas of triangles, rectangles, trapezoids, and circles. Problem 50 gives an approximation of pi of 3.16, compared to the exact 3.1416, by calculating the area of a circle with diameter 9 as 8/9 diameter, caret 2. This approximation was sufficiently accurate for architectural needs. The Egyptians developed formulas for the volume of pyramids, 1/3 base area height, and truncated pyramids. The Moscow Papyrus, around 1850 BC, contains problem 14, which calculates the volume of a truncated pyramid with a square base, a formula that the Greeks would rediscover later. This geometric mastery enabled the construction of the Giza pyramids, whose stone blocks, weighing up to 80 tons, were cut with a precision of 0.5 mm. The Egyptian algebra, solving the unknown. The Egyptians used a method called AHA, or how, to solve linear equations. The term AHA means quantity or heap. Problem 24 of the Rhind Papyrus asks, a heap and its seventh give 19. What is the heap? The method involves assuming a value, e.g., 7, calculating the result, 7 plus 1 is equal to 8, then adjusting by proportionality, 19/8 7 is equal to 16.625. This technique, called the rule of false position, is the ancestor of modern algebra. Arithmetic problems include calculations of sharing, proportions, and progressions. Problem 40 of the Rhind Papyrus deals with an arithmetic progression. Divide 100 loaves among 5 men, so that the shares are in arithmetic progression and the sum of the two smallest shares is 1/7 of the sum of the three largest. The solution involves a system of linear equations. Egyptian astronomy. Observing to govern Egyptian astronomy was inseparable from religion and pharaonic power. The pharaoh was considered the son of Ra, the sun god, and temples were designed as replicas of the universe. The pyramid texts, Old Kingdom, around 2400 BC, contain descriptions of stars and constellations, including the Big Dipper, called the Thigh, and Orion, associated with Osiris. The astronomical ceiling of the tomb of Senenmut, around 1470 BC, is one of the oldest known star catalogues. It depicts the constellations visible in the Egyptian sky, with divisions into decans, 36 star groups, used to measure time at night. Each decan rose about 10 days after the previous one, creating a stellar calendar. The Egyptians also used instruments like the Merkit, an alignment instrument, and the Bay, a plumb line, to determine north-south orientation. The debate on the origin of Greek mathematics. The question of Egyptian influence on Greek mathematics is a subject of debate. Ancient authors like Herodotus, 5th century BC, Diodorus Siculus, 1st century BC, and Strabo, 1st century BC, report that Greek philosophers, Thales, Pythagoras, Plato, Eudoxus, studied in Egypt. Thales of Miletus, around 600 BC, is said to have learned geometry in Egypt and measured the height of the pyramids using shadows. Pythagoras, around 570 to 495 BC, is said to have spent 22 years in Egypt, according to Iamblichus, 3rd century AD. However, modern science historians, like George Gevorgys Joseph, argue that Egyptian influence has been systematically minimized by Eurocentric narratives. Egyptian mathematics was as sophisticated as that of the Greeks, but